Okay, we are still here in our topic, external flow, forced convection. So here's another problem. A long 10 centimeter diameter steam pipe whose external surface is 110 degrees Celsius passes through some open area that is not protected against the winds. Determine the rate of heat loss from the pipe per unit length. So heat loss per unit length. This is per unit length. And 10 degrees Celsius and the wind is blowing across the pipe at a velocity of 8 meters per second. Okay. So first, let us, for the solution, let us have some illustration of this one. So say this is your pipe. So say this is your pipe. Okay. And the this is a long pipe supposedly, and have a diameter of 10 centimeter. Whose external surface temperature of surface is 110 degrees Celsius. Passes through some open area that is not protected against the wind. So there is a wind flowing through this area. Determine the rate of heat loss. So let us determine the heat loss from the pipe per unit of its length. So we need to determine the heat loss per unit length. When the air is at 1 atm pressure, so the condition of your air, the pressure is 1 atm and 10 degrees Celsius. Okay. The wind is blowing across this pipe at a velocity is 8 meters per second. Okay? So based from here, since we need to determine the heat loss per unit length, then we need the what I call this. We need to determine the needed equations and so on. Okay, so our heat loss is equal to, again, what is our heat loss? It is equal to HA T surface minus T fluid. So we have our Q is equal to H our A, the area, the surface area of this pipe is given by what? It's given by pi d times its length, right? Right? To determine the surface area, we have pi d times length, okay, of this pipe. Then ts minus t theta. Okay, and to determine the per unit length, all we need to do is to get its per unit length. So we have a per unit length here. So therefore, our needed equation for heat loss per unit length is H pi d ts minus t fluid, wherein our H is unknown. Then our diameter is what's our diameter? 10 cm or 0.1 meter, right? So we need to convert it first. 0.1 meter. Then our T surface is, I think it's 110 110 minus 10. So we have 100 degrees C. So 110 minus 10 is 100 degrees C. Okay. So we need once again to determine the value of our H. And like what we did last time, first thing first is to, in order for us to use the correlation and use the Nusselt number to find the H, need to know the properties of our air by having the value of our film temperature, which is the average of your surface and your fluid. So therefore, our film temperature is 110 plus 10 divided by 2, is that we have, this is 120 divided 2, this is 60 degrees Celsius. So if this is our film temperature, to get the properties of air, we need to go back here. So we have a property of air at 1 atm pressure. So this say that the air is at 1 atm. So we can now proceed to the temperature, film temperature, which is 60. So if we have 60, we have this following properties. Right? Okay. If we already determine the properties using TF, then we can now solve for the value of our Reynolds number, wherein our Reynolds number is once again given by the V, the characteristic length all over V. Okay. So if you notice, since our condition now is cylindrical surface, right? Cylindrical surface. So based from what we've studied last time, our RE, if we have a cylindrical surface, is given by this. Okay, so we have the value of your what you call this? Value of our stream velocity is given by the problem, this one. So we have 8 meters per second velocity of the wind, and then our diameter is 0.1 meter. Then our viscosity is, what is our viscosity? Kinematic viscosity V is 1.896 times 10 to the negative 5. So we have 1.896 times 10 to the negative 5 meters square per second. So as you can see, the check can cancel 1, 2, 2, SS. Okay, so we have now a dimensionless number RE, which is equal to 42,190. Okay, and if we can also recall based from our discussions, so please go back to your notes, then and then get the critical Reynolds number for this condition. Okay, so in our condition, our critical Reynolds number is 200,000, or based from our discussion like last time, it is 2 times 10 to the 5, right? So we have a 200,000 critical, and our RE is less than, therefore our flow is laminar. Okay, and since our flow is laminar, we can now have the can now have the all this the NU for laminar flow is equal to H average D all over K, or based from the formula, we can also using the the cylindrical surface. So we have a C, R, E, M, P, R, 1/3, right? So, so we will gonna use this wherein our C and M is our constants. And if you gonna review also your notes, I have also given the value of our C and M for a value of C and M for a certain range of RE, right? From I think from 4 up to 40,000 to 400,000 Reynolds number yon. Okay, so since our Reynolds number is 42,000, then when you look at the table that I have already discussed last time, then if you're gonna select this, so this is from 40,000 above, then you can now project the value of your C and your M. Okay, so having that, the value of our C, based from my given table last time, is value of our C is 0.02808. I mean 0.027. Okay, and then our R is 42,190 raised to M. Our M is 0.805, this one, and then multiply by PR, which is can also be found here. PR, this one. So we have 0.7202. 0.7202. Okay, and from here we have the H, and our characteristic length is 0.1 meter, and our K can also be found here in our table. Our K is 0.02808. 0.02808. Okay? And based from this one, you can now solve for the value of our H by having some alterations of your algebra here. Then you can get a value of H around 35.9 watts per meter square K. Okay, and if you're gonna solve this on your own, then please complete the following units so that we can easily see the units of our needed values. Okay, so for H we have 35.9 watts per square meter K. Okay, and then finally, since we already know the value of this, we can now go back to equation 1 so that we can use this value and solve for our Q. Okay, so here we can now solve, since we already knew this 35.9, multiply by this thing, and then can now see that the value of our Q per unit length, heat loss per unit length, is equal to 1128 watts. Okay, so that's all. So that is all about this convection heat transfer in a external flow and at cylindrical surface. Okay, so thank you so much.